What I want to do now is show you and teach you how to derive our next trig function, which is going to be our reciprocal of sine, which is cosecant. Okay, and my approach that I want to take with you is I first want to derive a substantial number of points for sine, and then it would be quite easy to find the cosecant points because sine, as you can see here, is the reciprocal of cosecant. So once I find my sine values, I could just take the reciprocal and then get these guys, and then we can go ahead and graph it and see what it looks like. All right, and then over here for our convenience, I've just cut and pasted the unit circle, and then down here I wrote down two identities that we learned earlier in chapter 4, and this right here means that sine is odd, which you learned, and this also is a cofunction. Sine of theta plus pi is going to be negative sine of theta. Okay, and you'll find out what we're going to use that for here in just a few seconds. All right, so let's just go ahead and derive a number of points here, and then you'll see what's going to be so important about all these points here. Okay, so let's just start with 0. Okay, if 0 is theta, sine of 0 is just 0. And I'm going to go to the left here. I'm going to go to negative pi over 6. Negative pi over 6. Well, the sine of negative pi over 6 is the same thing as the sine of pi over 6, and then just opposite. So sine of pi over 6 is 1/2. So opposite of 1/2, and so that's why it's going to be negative 1/2 right there. Okay. Now let's go ahead and do pi over 6. Sine of pi over 6 is 1/2. And then I'm going to go ahead and do sine of pi over 2, which is 1. Okay, so if you're wondering why did I choose pi over 6, 0, negative pi over 6, and pi over 2, why did I skip pi over 4 and pi over 3? I guess the only reason why that I skipped those was because if I took the sine of pi over 4, see how it's root 2 over 2, it's going to be some decimal. And if I did pi over 3, it's going to be radical 3 over 2. I'm trying just to stick to the nice numbers. And but we could have done those and then try to get approximate decimals. But really, that's the only reason why I did that. Now, in order to get the rest of my points here, I'm going to do this really cool trick, all right? And I'm going to show you this trick because normally you wouldn't have the unit circle in front of you. I'm just showing you how to do the trick with the unit circle in front. So that means you can kind of see very quickly and verify what I'm doing right now. So I'm going to use this next identity called the cofunction identity, in which is if I take my theta, okay, sine of theta, so like sine of theta, I'm going to take my first one, negative pi over 6. If I take that, and if I add pi to it, negative pi over 6 plus pi is 5 pi over 6. Okay, and you can see that from right here. This is negative pi over 6. If I add pi, just go straight across. See how I'm at 5 pi over 6? Okay, now this is what's really neat about this, okay? So I just took negative pi over 6 and I added pi, and I got 5 pi over 6. Well, that is going to be equivalent to the sine of theta, but then the opposite of it. Well, look, we already took the sine of theta, which was negative 1/2. So this value is going to be the opposite of this. So it's going to be 1/2. And as you can see on the unit circle, it's 1/2. Okay? So I just use this identity to just derive another points. Okay? Now let's go to 0. Add pi. Okay, so I'm going to plug in 0 right here. 0 plus pi is pi. And I know it's going to be the opposite of this. So it's just going to be 0. See? And we're just going to continue this pattern here. I'm going to take pi over 6 and I'm going to add pi. Well, if I add pi to that, it's going to be 7 pi over 6. And again, you could verify that. Go to pi over 6 and then go down. See how it's right here? But you could also do the math and just add pi. I know that that's going to be the opposite of this. So it's going to be negative 1/2. You see? Not too bad? Now let's go to pi over 2. If I add pi to it, it's going to be 3 pi over 2. And I know that it's going to be the opposite of this, so negative 1. So this is really neat right here. This gives us many different points without having to have the unit circle in front of us. All these cool tricks. Okay, let's see. Let's go to 5 pi over 6. If I add pi, let's see if I add pi to that, that's going to be 11 pi over 6. I'm kind of running out of room here. And that's going to be the opposite of 1/2, which is negative 1/2. And one more, if I add pi to pi, that's going to be 2 pi. And then the opposite of 0 is 0. Okay, so we've just done one full period, right? We went around the entire unit circle. So the way that we derive now our cosecant values is I just take the reciprocal of these. Okay, so for example, theta stays the same, so negative pi over 6. And what's the reciprocal of negative 1/2? Well, it's just negative 2. Okay, same theta value as that theta, 0. But what's the reciprocal of 0? Well, let's think about that. 0 is the same thing as like 0 over 1 or 0 over 2 or 0 over 3. Well, if I flip 0 over 1, that's 1 over 0. And we can never have a 0 in the denominator, as we know. So that means that this right here is going to be undefined. So I'm just going to put a U for undefined. Okay? There is no value at 0. And we'll talk about what that looks like graphically in a moment. And now I'm just going to quickly now do these. So reciprocal of that is 2. Pi over 2. Reciprocal of 1 is just 1. 5 pi over 6. Reciprocal is 2. Pi is going to be undefined. 7 pi over 6, negative 2. 3 pi over 2 is going to be a negative 1. 11 pi over 6 is going to be negative 2. And then lastly, 2 pi is going to be undefined. Okay, so we have a substantial number of points here. And what I want to do now is actually plot this. Okay, and I'm going to still put the same coordinate points as I would if it was a sine curve. So I'm going to go ahead and do pi over 2. I'm sorry, pi over 2 pi. Okay, that makes more sense there. Let's see, 3 pi over 2 and 2 pi. Okay, so first what I want to do is this. Can I go ahead and at 0, at pi, and at 2 pi, we have undefined values? Well, undefined means we either have a hole or it's going to be an asymptote. And for this case, they're going to be asymptotes. And actually, they always will be. We're not doing any holes here because we didn't cross anything out. So I'm going to put an asymptote at 0. I'm going to put an asymptote at pi. And I'm going to put an asymptote at 2 pi. If you're like, whoa, dude, this is far out. Heck yeah, this is what I'm talking about. Okay, so there we have our asymptotes. All right, well, now we're ready to start plotting points here. So let's see. Negative pi over 6. Let's think about this. Say if this was a unit circle, this would be 0, pi over 6, pi over 4. I'm sorry, yeah, pi over 6, pi over 3, and then so basically I'm just gonna cut this into thirds. So pi over 6 would be right here, okay? And I'm gonna make this right here 1. I'm gonna make this right 2, and this would be negative 1, and this would be negative 2. All right, so let's go to the point negative pi over 6, which is then going to be right here, negative pi over 6, negative 2. So I'm going to go right here, negative 2. So I'm going to put a dot right there. And maybe I'll change my color there so it could be a little more distinguishable. Okay, 0, so there's nothing there. Pi over 6, 2. So pi over 6, 2. And then we'll go to pi over 2, 1. Pi over 2, 1. And then look at 1 pi over 6, 2 pi over 6, 3, 4, 5. So this would be 5 pi over 6 right here. So that's why this is going to be my 5 pi over 6. I'm going to put that right here, 5 pi over 6. And I'm going to go to 2. Okay, and it creates this U-looking graph. Sorry that I was butchered up on this tablet here, but I try my best there. Okay, let's keep going here. At pi, there's nothing right there, so let's go to 7 pi over 6. 1, 2, 3, 4. Well, look, that's 5 pi over 6. That's 6 pi over 6, 7 pi over 6, right? So that's going to be right here. So I'm going to go to negative 2. And then go to 3 pi over 2, negative 1. And then this is a 7, 8, 9, 10, 11 pi over 6. So right here, I'm going to go down to it there. All right, not bad, I guess. Okay, and so what we have just graphed is one complete period of the cosecant function. Okay, and as you can see, there were a lot of points. It wasn't as quick and as easy as the sine curve, but let me show you something real quick that may just blow you away. Check this out. I'm going to go ahead and graph the sine curve right now, okay? I don't know if you noticed this, but do you notice the similarities in the sine curve and the cosecants? Notice that the zeros, okay, notice that the zeros of our sine curve are our asymptotes, you see, and our max and our mins, okay, let me just get this over here, and our max and mins, okay, our max and mins of our sine curve are going to be basically our max and mins of our cosecant. And actually, this thing is just gonna keep repeating. So I'm just gonna draw little sketches now. But like over here, you would have something like this over here, and then like over here, we just did 1 point, but this thing would continue on. This would do this over here as well. You know, another asymptote, and the pattern would just continue. And since this, you know, it takes up so much room here, 1 period is usually enough. But, you know, sometimes you might want to do 2. And 2 could be this guy plus that guy right there. All right, so that's basically the framework of it. Let me just review now the cosecant function before I end this video. And that is the following. Okay, this is a much nicer piece that I just did right now. So obviously right here, the gray line is our sine curve. The cosecant curve looks like this, which we just derived. And here are a few things that I just want you to write down. You might want to pause it and just write this down. That 1 period of the cosecant is 2 pi. That the domain are all real numbers except at 0, at pi, at 2 pi, at 3 pi, or known as at n times pi, where n is an integer. And the way that you write that down, you say n is within the integers. Okay, and you kind of write this as a little set notation like that there, okay? And the range, again, this thing goes down forever, so it's from negative infinity to negative 1, stops at negative 1, but then there's nothing from negative 1 to 1, so that's why we'll go, there's nothing from negative 1 to 1, and then it comes back up, so it's our range. And notice that the domain and the vertical asymptotes are going to be the same. Vertical asymptotes at the zeros of sine, and this thing is symmetric at the origin. Okay, meaning that if whatever this point is right here, then that means it's just going to be the opposite of the x and the y over here. Okay, and before I let you go, let's just write down what are the key points. Okay, and notice that this is just going to be at just a half a period. And so the key points, and you only need 5 here, is going to be 0, pi over 6, pi over 2, 5 pi over 6, and pi. Okay, and those values are going to be undefined, 2, 1, 2, and undefined. And you'll find out why we only need 5 in the next video.